2.5, connected particles. So by connected particles, we're going to split this up into different sections. All the work that we are doing at AS in mechanics, your particles will be connected either horizontally or vertically. We also have pulleys to look at. We have things like lifts to look at as well. But in this section, we're just looking at things like a car connected to a caravan. So that's what we mean by connected particles. And we consider each particle separately. So if you've got your head around F equals ma in the earlier examples, then it's exactly the same here. What we're working on is that when the particles are moving in the same straight line and they remain in contact with each other and they're connected by an inextensible rod or string, then we can consider the system to be a single particle, and we'll go into that in a little bit more detail through the examples. So, Newton's third law of motion: for every action there is an equal and opposite reaction. So all of this is based upon that idea. We've also got Newton's second law up in the corner here, so that's Newton's second law up there. And so we're going to be applying both of those. And so we'll reference Newton's third law as we do the example. If you follow these 6 points that we have here, and it's the same, exactly the same in your notes, then you will not go wrong. You can almost treat this as a recipe on how to do these types of questions. There's quite a lot of work involved, but once you've practiced them, it's the same method every single time. So you should be all right with this. As always, draw a diagram with the tension acting towards the centre of the string. So this is where Newton's third law of motion comes into play. When we've got something connected, so two particles connected by a piece of string, there will be a tension in that string that is pulling on this first particle A, and there will be an equal and opposite tension in the string that's acting on B, and that's Newton's third law of motion. So that we've got this equal and opposite reaction going on here. Okay, thrust acts away from the centre of the string because thrust is a pushing force, tension is a pulling force. I mentioned that right at the start of the chapter. If you've got a thrust, it's generally, rather than a string, we'll be talking about a rod. So a car caravan situation where you've got something solid between the two particles, then you would end up with a pushing rather than a pulling. For example, if the car that was pulling the caravan put the brakes on, then there would be a thrust within the rod as the caravan tried to bash into the back of the car. We also need to consider modelling here when we're talking about this tension, and this is really important that you get these two the right way round. And in your notes under example 2.5.1, we've got modelling assumptions made, and these are the two modelling assumptions that we have. So inextensible means that it does not stretch under the load, and the way that we use that information is the acceleration is the same in both objects. Okay, so when we have got, it will say the word inextensible within the question, then we can take the acceleration of both particles to be exactly the same. When we're modelling something as light, so we've used this idea of modelling as light before, where we're ignoring the mass. In terms of our string, it means that the tension is the same throughout the string, which is what I've got drawn here, where I've put my tensions equal. So what we're going to end up with is, if we were moving in that direction with an acceleration, particle B would have exactly the same acceleration, and what that means is we've got two variables and we can set up two equations, therefore we can do simultaneous equations. Okay. Number 1, draw your diagram. Number 2, label and identify forces acting on each object. Number 3, identify the direction of motion or intended motion. You might be stationary and about to set off. Number 4, write down F equals ma for each object. At this point, you can consider the whole system. I am not going to do the working out by working it that way. I will mention it as we do the examples. I'm going to stick with writing F equals ma for both objects. I think considering the whole system is something that maybe you will look into as you get more familiar with the topic. If you do physics, you probably have set it up by considering the whole system, which is absolutely fine. As long as it's really clear what you're doing and you're getting it right, it doesn't matter which way you go. Number 5, solve simultaneous equations. So for number 4, we're writing down 2 Newton's second laws of motion, 1 for each particle. Number 5, we're going to solve them simultaneously because T and A are common to both. And then number 6, we'll worry about that later. That's more problem solving if we're asked to go a little bit further within the question. Let's have a look at our first example. Okay, so we have got 2 particles, A and B. The first thing that you need to do is take all this information from the table and apply it to the particles. So if we look at particle A, we've got a mass of 3 kilograms, which means there's going to be a weight, and the weight will be 3g. We have a reaction. I'm going to call it reaction of A because the reaction on this particle will be different to the reaction on particle B. And resistance to motion is going to be 6 newtons. Now the reason I know it's going in that direction is because B is the one with the driving force. So that driving force, we don't have a driving force on A, so it must be that B is the particle that's pulling. So we have that driving force going forward, which means resistance, the direction of motion, is going to the right for each particle. Therefore, resistance has to be going in the opposite direction. So resistance for motion on B is 10. B has a weight of 5g newtons, and there is a reaction. So they're all the forces that we've seen before and that we can pull out of that table. Then the other force that you have to add in is this idea of tension. By Newton's third law, it is equal and opposite, and because we're told this modelling information here, connected by a light inextensible string, then we are applying these 2 modelling situations. And in an exam question, you may get asked at the end of the question, how have you used the information that the string was inextensible, or how could you improve on the model or make it more realistic? And so it's referring to these 2 situations. Because we've got a light string, our tension is the same throughout, and because it's inextensible, our acceleration is the same throughout. So we end up with this system. To set up F equals ma, we're going to just focus on particle A. So we'll just ignore particle B for a minute. So you almost can split them down the middle. So focusing on particle A, we are moving to the right. Remember, that's our motion. So our resultant force, tension, is going in the direction of motion. We don't know it, so I'm just call it T. Take away the resistance, which is 6, is equal to mass times acceleration. The RA and the 3G, we're not going to be including those because we're focusing on the forces that are moving in the direction. Anything that's perpendicular can be ignored. If we look at particle B, so we have in the direction of motion, we've got a force of 40. Against motion, I've got a force of 10, and I've got the tension. So I'm taking both of those off, and it equals mass times acceleration. So we end up with 30 minus t equals 5a. So we can set up F equals ma on each of those separately. So you just work with them separately. So that's no different to what we've looked at before. Force in the direction of motion, take away force against motion, ignore any force that's perpendicular. Because of our light inextensible string, we have T is common to both of these equations and A is common to both of these equations. So these are simultaneous equations. And they're easy simultaneous equations, a lot easier than what we see in pure maths. What will always happen here is because these 2 tensions are equal and opposite, you will always get one in one of the equations that's positive and one that's negative, because the direction of motion is the same for both particles. So the easiest way to solve these 2 is to add them together. So to go back to the first way that you learnt simultaneous equations back at GCSE, where you've got an opposite sign and then you can just add them. The coefficient of tension will always be 1 as well, so it is quite straightforward. So what we've got is 30 add minus 6 is equal to 3a add 5a. Nice and straightforward. We can then have a look at what the tension is. So I'm going to go in equation 1, just because my tension is positive there. Why would I try and use a negative if I could have a positive? So substitute the 3 into equation 1. So tension is equal to 15 newtons, and then you should automatically be doing a check. So if we just put the check in, you can just see that that is the case, and therefore we know we've got it right. Do be clear with your working out. If you notice, when I wrote down F equals MA, I haven't calculated 40 minus 10, even though I can do that in my head. I've written it down. There are two reasons. That equation picks up the marks for using F equals MA correctly. But also, if you have a clear diagram, when you get towards the end of an assessment with a question like this on, if you've got a little bit of time, you won't have time in the exam to go back through every question and read everything again. But if you have really clear diagrams with all your forces on, it is really easy to go back to your equation and look at what we've got in terms of this diagram and say, right, I've got 40 going that way, I've got 10 going that way, I've got t going that way, 40 minus 10 minus t equals mass. And so you can just do a really quick check. The marks for mechanics are in setting up these equations, not for this bit, because this bit is basic algebra. It's these equations where all the marks lie. So this bit down here, you're talking about 2 marks maximum, whereas up here, we're probably talking between 4 and 5 marks just for those 2 equations. So you've got to get them right. If you get one of them wrong, if you miss one force out, you don't get any marks for that equation. If you don't set these 2 equations up and get the method marks for it, you can't get the easy marks in this solution here. You've got to get these equations right. Otherwise, you just throw 6 marks away easy. If you can check on your diagram, then that will make it a lot easier. I'm not interested in that bit, I'm interested in that bit, and that's where your check needs to be. If you wanted to do this all in one, so if we were just looking for doing this all in one system, so we would, what happens is when we do the 40 minus 10, we've got minus t plus t minus 6 is equal to, you would add the masses together. So you would end up with that, and those 2 are cancelling out because of the minus t and the plus t. So that's kind of treating it as one system, which you can do. If that doesn't make any sense, don't do it that way. I would stick with this, because the problem with doing it that way is you still need to find the tension in the string. So you still have to set up one of these 2 equations here. So you still have to write 2 equations, whichever way you choose to do it. Okay, so the only advantage to doing it this bottom way is if you just asked for acceleration and you're not asked for tension. Otherwise, I'd just recommend going for the 2 particles. So having a look at example 2.5.2, read through the question, pause the video, have a go at putting all the forces onto your diagram, and then have a go at setting up F equals MA. Join back into the video at the point where you feel you need a little bit more support. If you can get to the end of the question, then that is brilliant. You'll be able to skip ahead, but do check those equations and make sure you are showing enough working out. So we have got something that's being modelled as a light inextensible string. So light inextensible string means that the tension is the same throughout, and it also means that our acceleration is the same. The truck's engine produces a constant driving force of 2,500 newtons, so that will be in the direction of motion. And then we've got a resistance, so the truck has got 750 and the car has got 400 newtons. So we have our system set up that way. I am going to be splitting them into 2 equations. So I'm going to focus on the truck first, so using F equals MA, in the direction of motion, which in this case is going to the left, I've got 2,500 newtons, resistance is 750 and there's a tension that's acting against our motion is equal to mass times acceleration. For the car, I'm using F equals ma. It's always a good idea in any part of maths, but particularly mechanics, to state any equation that you're using just to make it really clear, so that if you do make a slip up, you might still stand a chance of picking up your method marks. In the direction of motion for the car, we have tension. Against motion, we have the resistance of 400, the mass is 850, and acceleration is a. So I've got these two equations here. So if you haven't paused the video at this point, pause this now and have a go at solving these two equations. I'm going to add them together. So we have, when we simplify all the numerical values down, so I've got 2,500, take away 750, take away 400, which is 1,350. The t's have been eliminated, and because I'm adding, I've got 2,350 lost the 2. So we can work out that acceleration is equal to 27 over 47, which is equal to 0.57 to 2 significant figures. It's particularly useful to give an exact value just in case you need it later on in the question. To find the tension, I'm going to substitute into 2. So adding the 400 across, we've got 888.3. So giving that to 2 significant figures would give me 890. It's really important when you're doing an exam question to label the parts of the question, and in the majority of maths you have to label it under the correct part. You can't mix your parts together. It was mentioned in the last question, but with this topic, A and B can be answered together because this working out is interchangeable, but I would just put at the side an A and a B like that, just so that I'm showing that I know that I'm trying to answer both of those at the same time. If you found tension first and then found acceleration, they wouldn't down mark you for that. You don't have to do it in the order of the question. Quite often the question is asked to find the tension first and then acceleration. If you're using this method, you would find acceleration first every time. So that's the situation that we have got for parts A and B. Moving on to part C. So when the truck and the car are travelling at 22 metres per second, the tow bar brakes. If the magnitude of resistance to the motion of the truck remains at 750, calculate the time difference in achieving a speed of 30 with and without the car in tow. So let's start with. So time. As soon as we see time, velocities, any of that, we know we're thinking SUVATs. So if I write my SUVATs out for this question, what do I know? So this is with the tow bar. We're starting at 22 metres per second and we're trying to go to 30. The question's asking about time. I know the acceleration because I calculated it earlier. So the acceleration, I'm going to use its exact value of 27 over 47 just to keep accuracy. If I use 2 significant figures here, that means that I'm going to lose some accuracy with my final calculation. So I want to keep accuracy. I'm going to use the exact value from earlier. So V equals U plus AT. We have 30 equals 22 plus 27 over 47. And calculating time from there, we've got 13.93. Again, I've got more significant figures than I know I'm going to need because that's not the final answer, that's just this first section. So what does it mean without the car in tow? So if the car is not there, the situation is going to change, and the main thing in terms of the truck and looking at that force diagram is that that tension has gone, because I don't have a tow bar, I haven't got something pulling on it. So almost think about it, if you take the car away, then the truck is going to speed up because it doesn't have something pulling back, which is what that tension was doing. It was a resistance to motion. So the car has gone, and I'm now travelling at 22 metres per second in that direction. And therefore, if we take the car away, we're going to accelerate, but that acceleration is going to be at a different rate. So if we consider F equals ma, so this is for without, so without the tow bar, we need to recalculate what our acceleration is. So when you do all of these questions, the thing that you need to be asking yourself is, has the system changed? If the forces have changed, then the acceleration will have changed, because you've got a completely different system. So working out F here, it's the same idea. We're moving in that direction. So I've got 2,500, take away 750 is equal to 1,500 A. So I can recalculate what that acceleration is, and you should get it to be 7/6. Again, I'm using exact values just because this is part of my working out and not my final answer. The working out for this bit is exactly the same as it was previously. So we've got 22 and 30. It's the acceleration that is different, because that is what has changed with the system. By changing the forces, F equals ma, acceleration is the only thing that links between these two topics. So it's the acceleration that's changed. The rest of the working out here is exactly the same. So we can just write down what we did last time. Obviously, when we solve it, we get a different value for t. So I've got 6.86. Therefore, to answer the question, and it's always a good idea to check at the end of your working, because there's a lot of working out with these types of questions. So just check that you've actually answered what the question is. So the difference in time, which is what we were asked for, is 13.93 minus 6.86, which is 7.1 seconds. And that is where I'm going to two significant figures for that final answer.